Hey students, welcome to Psych 652 Lab, module number 7, where we're going to be talking about statistical inference and simple linear regression, also known as SLR. So today's lab is going to be pretty unique. We're not going to be downloading any data sets, but we will be simulating our own data sets. And the purpose of this is so that we can simulate the population data and pull samples from it and see how we can make inferences from those samples towards our population. So let's go ahead and just get started with going into R. Let me go ahead and turn my mouse on real quick. There we go, so you can see where I'm at all times. Perfect. All right, so we're going to go and open up R Studio. So I was recently told that sometimes my text is a little bit too small, so I went ahead and enlarged my text and zoomed in on the screen so you can have an easier time reading it. So let's go ahead and open up a new R project. But I'm going to let you be honest with you, we don't technically need a project for this lab because we're not downloading any data, but I think it's good regardless of whether or not you're using data or not to always have a project file because I think it just keeps you so organized. So we're going to go ahead and still continue with our same course and create that project file. So go ahead and make sure it's saved to the correct subdirectory, and I'm going to name it module 07 and go ahead and create project. While that's happening, I'm going to go load up some notes here. Perfect. Okay, so now that we've got our project created, let's go ahead and create a new R notebook and delete this unnecessary text. Perfect. And we're going to go ahead and name this notebook today Statistical Inference in SLR. Let's go ahead and create that table of contents. So enter tab, colon, enter, TOC, colon, yes. And I'm going to go and save my notebook as well. And I'll name this Module 7 Notebook. All right. So today we're not going to be installing any new packages. Let's go ahead and load our libraries, actually. Load libraries. Oops, works. Load, sorry everybody. Load libraries. And go ahead and insert a new archive. We're not going to be downloading any new libraries, actually. We're going to be just using the psych package, if I could spell. Library psych. And library, my favorite package, the tidyverse package. So luckily we don't need to install any new packages today. So go ahead and let that run. Nope. Okay, looks like it worked out. And I'm just going to go and play it again so that we can get rid of that text there. Okay, so again, we're not going to be reading in any data because we're going to be simulating our own data set. And today the data set I wanted to create is, imagine that we have some sort of intervention aimed at helping people to lose weight. And in that intervention, we kind of are going to imagine today that we can apply that intervention to the entire population and see how they performed on the intervention and how many pounds they lost today. And we're going to be creating that population. And essentially, we know that that's never possible to really get the whole population to see how everyone would react in that intervention. But the nice thing about simulations is it gives us the ability to see, say, what if that happened? What if we're able to do this to the entire population? So we're going to set some parameters to our population and make sure that and then pull some samples and see how we're able to make inferences from our samples to our population. And we're going to do that by generating some data to start off. So let's go ahead and write some notes. So let's go ahead and do hashtag consider pounds lost, so LBS, LOST, in the hypothetical population. And then we're going to do two hashtags. Let's go ahead and simulate the population. Like I said, we're going to be simulating our own data sets today. And I'm going to insert a new R chunk. So the first thing we're always going to do whenever we simulate a population or run any sort of simulation study is usually set a seed. So it's set.seed. And what this does is essentially confirms that every single time that we run this simulation, we're going to get the same results every time. And additionally, because we're all running this simulation together, it's going to confirm that we get the same output every single time. So we're going to set our seed to 8642. There's really no reason I chose that number. It's a completely arbitrary number that I chose. Now, the next few things, it's okay if you don't completely understand what's going on with them. I'm just going to be explaining what's going on and what was happening when we're simulating this data set. It's totally okay if you don't understand it. The important thing to know is that we are creating a population data set. But I'm going to go ahead and kind of talk it through as to what's going on. So the first thing we're going to do is we're going to name a new object. It's going to be called P underscore LBS lost. And that's going to be for the population pounds lost. So the amount of pounds lost in the population. And we're going to use a function called rnorm. Now, rnorm takes a few different arguments here. So the first one we're going to set is an n equals. We're going to set this to 50,000. So what this means is we're going to create a data set with 50,000 observations. Then we're going to use mean equals. And what this is within that population or in that data set, we want the mean value to be 3.00. Additionally, we're going to use SD equals, and we're also going to set what the standard deviation is. And we're going to set that standard deviation to 2.00. And so we're going to set a list of 50,000 populations, so 50,000 participants. Next, we're going to go ahead and create a new object called my underscore pop, standing for my population. And we're going to say data.frame. And we're going to do parentheses P underscore LBS lost. And what that's going to do is this is going to initialize a matrix value, and then we're going to turn it into a data frame so that we can do more analysis on it. So what I'm going to do is I'm going to run this one line at a time. First, I'm going to run the set the seed to 8,642 so that we can have the same results. I'm going to go ahead and press run here, and it's going to create this matrix of 1 to 50,000 observations. Then when I run this line of code, it's going to turn this into a new data set called my underscore pop. And that's all there is to it. And I'm just going to go ahead and run it all at once just to make sure we get that seed correctly nailed in there. So we go ahead and do that. So we have a new data set with a variable called P underscore pounds lost. So that stands for the population pounds lost, and it has 50,000 observations in it. So we finished. So you've gone ahead and you've simulated your first data set. So congratulations, good for you if you're following along. Okay, so the next thing we're going to do is we're going to go ahead and describe the data. Hashtag describe the data. So what we do, go and do insert our chunk, and we're going to do describe my underscore pop. So we go ahead and do that. So describe my underscore pop, and go ahead and press play. So as we can see, we have a data set with 50,000 observations. The mean is 2.99. So we set our mean to 3.00. It got pretty close. It tried to make it pretty close. And our standard deviation of 2. Now another thing that's unique about this is that if we go over and we look at the skew, we have a skew of 0. That's because this rnorm function sets it so that we have a normally distributed data frame. So that's the beauty of it. We have a normally distributed data frame. And we can go ahead and check this even more by creating a histogram. I'm going to first go ahead and set this to the second level header. Then we're going to go ahead and create a third level header called create a histogram of the population. Okay. So let's go ahead, I'm going to go ahead and get this up here. Let's go ahead and create a histogram of the population. So we're going to insert a new R chunk. And we're going to use ggplot. So we do ggplot my underscore pop, comma, AES. And we're going to set our x equals to P underscore LBS lost. Remember, when you're getting a histogram, all you need is an x value. You only need one variable to be mapped to. And we're going to set geom underscore histogram. And then we're going to set a bin width, just so it looks a little bit nicer. So bin width equals, and we're going to set our bin width to 0.25. And that's just going to make it look a little bit nicer for us. And I'm also going to set some labels here, so then when next time we come back to it, we'll go ahead and we'll have a nice looking graph with labels to indicate what's going on. So we're going to go ahead and set our title. So it says pounds lost following a weight loss program. And I want to go ahead and set a subtitle too. Equals simulation of population. And let's go ahead and title our x-axis too. So each title and x-axis, you do x equals, and we're going to say, quote, pounds lost. Okay, so let's go ahead and play this. Okay, we're going to go 3 or 9. So look, as you can see, we have a normally distributed histogram here with our mean value and our median value, actually, because it's so normally distributed, at about 2.99. So we have the most values at about 2.99, and our mode is probably around the same as well, probably about 3. And additionally, it has a standard deviation of 2. So this is our population. This is how our population is distributed right now in this histogram. So we went ahead and created a normalized distribution within our population. So the next step that we're going to do is we're going to go ahead and take random samples from this population and see how they compare. And we're going to be focused mostly on the mean value. Say, what is going to be the mean value of our samples, and does it look very similar to the population? So let's go ahead and type in something. We're going to do a second level header and say randomly select 3 samples of size 100 from the population. Okay, so we'll go and insert, and this is again where we're going to go ahead and set another seed. So we're going to do set.seed, and for this one I want the seed to be 19657. Oops, 657. And that's again to make sure so we have reproducible results and we have the same results across everyone. So we set our seed, and I'm going to go ahead and just start off by doing this. We're going to go ahead and take a sample of this data set, and you might be asking, well, how are we going to take a sample of this? Well, luckily, R has this function called sample_n. And what that says is it takes a data set, so we want to get a sample from the my_pop data set, comma, and we want the size equals 100, which says we want the sample sizes you're going to take to be 100, and then we do something called replace equals true, and that's saying we want sampling with replacement. So every time it takes someone out and says this is one observation from my sample, they'll throw them back in so they have an equal chance of being chosen again. And there's reasons behind why we do that, but essentially we just know that we want to have sampling with replacement for this to work. So I'll go ahead and just run just this one, and then we're going to be doing the same thing to 2 other data sets, but I want to go ahead and just make sure we're understanding with just one data set, start off simple. So I'll go ahead and press play. And so we got a new data set called S1 for sample 1 that has 100 observations of one variable. So that's 100 samples, 100 observations taken from this mypop data set. That's essentially what it is. And as you can see, all it is we pulled from this mypop data set. So we're going to go ahead and do the same thing. I'm just going to go ahead and copy and paste this code to prevent any kind of error. So Control-V, Control-V, and we're going to name these objects into new things. So S2, S3. And I'm going to go ahead and press play again. And there we go. We have 3 new data sets, S1, S2, and S3. So S1, S2, and S3 that all have different samples of 100 in them. There we go. I'm going to go and press save. And now what we're going to do is we're just going to go ahead and describe each of those data sets already. So let's go ahead and get the mean value via describe for each sample. So let's go ahead and see how that works. So let's go ahead and see what our results look like. So let's go ahead and do describe S1. So we're just going to describe this S1 and see what the mean value is for that. So go ahead and press play. And look at that. We got a mean value of 2.93 with a standard deviation of 2.01. So if we look at what our original population value was up here, we say, wow, oops, let's go back. Wow, that's pretty close to our mean and standard deviation, actually. That's great. So we actually got pretty close to the actual mean. And we can go ahead and do this to the same thing. I'm going to just do Control-C, Control-V, Control-V, and then I'm going to do S2 and S3. And we're going to go ahead and look at all the means values of each of these as well. So as we can see, our first data set, it was 2.93. Our second data set, we got a mean of 3. So right at we got the exact same mean value, 1.85, a little bit different standard deviation. And then we got a mean value of 3.07 and 1.99. So as you can see, the mean values, although not exact all the time, we're pretty close to the population mean. And that's what we're kind of showing is like, hey, look, these are pretty similar to the population. So we're able to make inferences towards the population just by looking at the mean value. So we're going to do the same thing again, but this time we're going to make the inferences from simple linear regression. So what we're going to have to do now is we're going to have to create another simulation where we have two variables with certain characteristics with a slope and an intercept. Now I'm going to be honest, this next simulation is going to be a little bit more complicated, but what I'd like for you to do, I'm going to be explaining things as I go along, but just to copy it down, don't get too bogged down in the specifics of me creating the simulation, but go ahead and just copy down what I'm doing. And when we get to the activity assignment, don't worry, I'm not going to have you create your own simulation. I'm really just going to be having you copy and paste some code to create a simulation for yourself. Well, let's go ahead and start it. So we're going to create a new first level header called Inference for SLR. And then we're going to do hashtag simulate a population based on SLR results. So what that means is we're going to give a population a certain slope and intercept based on two variables. And our two variables are going to be pounds lost, which is going to be our y variable, and caloric deficit, which is going to be our x variable. So we're going to have caloric deficit predict pounds lost within a population. So let's go ahead and insert a new R chunk. And we're again going to go ahead and set a seed. For this time, I want the set.seed. So this time my set.seed is going to be 83587, and that's to ensure that we all get the same results when we run this simulation. Then I'm going to do caldef. So we're creating a new variable called caldef with it's going to be an rnorm function, and it's going to have 50,000. 50,000. So we're going to set n equals 50,000, comma. Our mean is going to be equal to 10.80. So the caloric deficit is going to be equal to 10.80. So that means the caloric deficit means the amount of calories lost. So how many calories under a normal caloric intake they've taken. So it's a little bit confusing when we get to the actual results, but just know that it's a higher number means less calories consumed. And then our SD equals 5.15. Okay, so here's the parts where I'm going to be doing some things and you're just going to follow along. We're going to go ahead and create a intercept that we want it to follow. So that's B0. Then we use an assignment operator. We want this to be negative 0.12. Then we want to set the slope to our simulation to be 0.29. Okay. Then we set sigma, which is just it's just pretty much error. We want to have some error of 2.1, and then we set our error in here again, but we make it so that it will run with our rnorm function. So rnorm mean or n equals 50,000, 3, comma mean equals 0, comma SD equals sigma. So don't worry that you're not understanding everything that's going on, but just go ahead and just type this out. If you have any questions later, come to lab and I can try and go over some of it with you. Okay, and then we're going to set our pounds lost with LBS, LOST, use an assignment operator. Then we do B0 plus. So this is setting up our regression equation for what we're going to have for our simulation, caldef plus E. So that's B0 plus B1, an asterisk for times caldef plus E, which is error. And then we're going to go ahead and save that all into a data frame. My underscore reg pop, and then do data.frame caldef, comma LBS lost. Okay, so assuming I did everything correctly, we're going to have a new data frame with two variables in it called my reg pop for my population regression, essentially is what that stands for. So let's go ahead and press play. Okay, looks like it ran successfully. So as you can see, we have a new data set with two observations, caldef and LBS lost, and we're going to use caldef to predict pounds lost within this data frame. Okay, so let's go ahead and save this. Okay, so now what we're going to do, now that the simulation is over, like I said, if you didn't understand everything that was happening in that simulation, don't worry, that's not part of it. We just needed to set that up so that we can get ourselves ready for the actual inferences part of simple linear regression. The next thing we're going to do, when we create, like for example, we created a histogram for our univariate analysis that we did earlier where we only had one variable, we're going to set a scatter plot now for the part where we have two variables to look at. So let's go ahead and do hashtag, hashtag, hashtag. Create a scatter plot for the population simple linear regression. So we have an actual population slope and intercept that we're going to be looking at for our regression analysis. So I'm going to go and insert a new R chunk. We're going to do GG plot parentheses. We name our data set, which is my underscore reg pop, comma, we set our aesthetic to, we need an X and a Y, so X equals cal def, comma, Y equals LPS lost, and then we use plus, and we're going to do geom point, and then we do plus, and then we're going to be setting a geom smooth layer, which is just setting a line on top, and we're going to use method equals quote LM, which is setting the best fit line. We're also going to do something called SE equals false. And this is essentially removing those 95% confidence interval bands that you would see normally. That's because we're just working with a really large data set, and I think it would take a little while if it had to produce those as well. And then we're also going to set a labs. So labs, we're going to set a title equals, and so that we can remember what's going on for later, we're going to say scatter plot of caloric deficit and pounds lost. And I'm going to go ahead and set a subtitle as well. Subtitle equals, and I'm going to put simulation of the population. So we know that this is a simulation, comma. And then we're going to do X equals caloric deficit. And then we're going to do Y equals pounds lost. Just so everything, oops, let's put this in quotation marks. Pounds lost. That way we just know that when we create this. So assuming I've typed in everything correctly, this should run appropriately. So let's go and run. Takes a little while to load. It's good, it's thinking. Perfect. Okay, so now we've got a regression line, and our regression is going to be somewhat similar to these up here. It might not be exact, but we should have a intercept around negative 0.12 and a slope of around 0.29. And let's go ahead and run that regression. But as you can see, this is what our regression slope looks like right now. So if we were to, and as you see, our slope is probably around negative 0.10, negative 0.12 or something like that. This is our x, our y, our intercept right here actually. It's not at negative 10, it's right here. Okay, so let's go ahead, and what we're going to do is fit a simple linear regression, which is something we learned last week about how to fit a simple linear regression. Let's go. So fit simple linear regression, SLR, model of the population. Okay, so let's go and insert R. Okay, so we're going to go ahead and create a new object called pop mod, use an assignment operator, and we're going to go ahead and just fit a simple linear regression line to this. So LM, so we do LPS lost, regressed on, CalDef, comma, data equals my reg pop, because we're using this data set to do the regression analysis on. And we save that into object, and then we also do summary pop mod, because that's the name of our object that we created. So I'll run this one line at a time. So I'll go ahead and do pop mod. There we go. So we have a large list. So remember, this is what our regression thing is. We use the summary function to get all the information we need out of it. So we're going to extract everything with the summary function. And voila, so we have it. So our intercept didn't quite end up being negative 0.12, but it was pretty close. So our intercept is negative 0.10 or 0.11 if we round up, and our CalDEF regression line is 0.28. So that means that this line has a slope of 0.29. So every 1 unit increase in caloric deficit is related to a 0.29 increase in pounds lost. And our intercept is negative 0.10, essentially, or 0.11. So our intercept is right here, and that's negative 0.11. Okay, and we don't need to focus on the F statistic or anything for today. We're just trying to see how this all works out. So we'll go ahead and press save. All right, now let's go ahead and get our samples from our myRegPop population. So we're going to use that sample N feature again to get samples. So let's go ahead and do insert R. And the first thing that first let's go ahead and title what we're going to do. Oops. Go ahead and title what we're going to do. We're going to do hashtag randomly select 3 samples of size 100 from the population. Okay, so let's go ahead and do this again. We're going to override our S1, S2, and S3 variables here. So we're going to do S1 equals sample underscore N myRegPop. So we're pulling from this myRegPop dataset, comma, size equals 100, comma, replace equals true. So it's the exact thing that we did before. So let's go ahead and just run this one and see what happens. So we're going to see this turn into 100 observations of 2 variables. We're going to overwrite that. Oh, nope, that looks like I misspelt it. Sure, some of you saw that coming. So we're going to go ahead and do that. So go ahead and run that. Oh gosh, what is going on? Oh, replace equals true. Oh, as you can see, okay. This is going to run this time, everybody. There we go. Now we have 100 observations of 2 variables. See, I mess up too sometimes. Okay, so as you can see, we got a sample of 100 observations from our data set. So it pulled from the myRegPop data set here. So let's go ahead and copy and paste that to reduce any errors, so I don't have as many errors as I did before. And we're going to go ahead and change this to S2 and S3. So for sample 1, sample 2, and sample 3, and it's just going to overwrite all 3 of these. Oh, and I forgot also, we didn't set a seed. So let's go and set our seed. So set.seed, and this one I want to be 1870. So that's going to just ensure. So sorry about all that kind of confusion, but this is exactly how your code should run. So you should first set a seed so that we all have the same results. Then you're going to run 3 sample ends on S1, S2, and S3. So let's go ahead and press play. Voila. We have 100 observations of 2 variables on each of these. And we have our seed set at 1870. Now, we're going to go ahead and set a simple linear regression to each of these models. So I just want to show you what S1, S2, and S3 look like. There's S1, there's S2, and here's S3. So let's go ahead and hashtag fit an SLR to each random sample. And again, these are completely random samples. So really, we're not really concerned about bias in our sampling techniques right now, which is great, which will never happen in the real world. But this is just a simulation, so we can say what happens if we have all the perfect parameters set here. So let's go ahead and start with our first linear regression model. So we'll do S1 underscore mod and save it to a new object. And we learned last week how to do simple linear regression. So LM there, and then we do LBS lost being regressed on CalDEF, comma, data equals S1. And we're going to start off by doing this with the S1 so I can show you what happens. So if we go ahead and press play here, we're going to get a new object called S1 mod, which is going to be that large list. And what we need to do is call a summary of this. So we'll do, well, actually, let's go ahead and just create all of our models first. So let's go ahead and copy. So you change this to S2 mod, and then this to S2, and then you change this to S3 mod, and our data to S3. Go ahead and run all 3 of those, and then we're going to get 3 different things here. So, whoops, that's the wrong one. S2 mod. So we get another large list with a lot of information. And we're going to go ahead and pull the summaries out of there. So let's go ahead and say hashtag get summary of our SLR models. Okay, so go ahead, insert a new chunk. And so what we're going to see is we're going to get numbers that are slightly similar to our regression line up here for our population regression, but they're not going to be exact. And they actually might be a little bit farther off than you'd expect. But the point is we're going to get around the actual values in the population. Let's do summary. And then we're going to do S1 mod. So we're getting the summary of this S1 mod up here, right there. Summary, S1 mod. And we're going to do this for the S2 mod and S3 mod, but I first want to just show you what the results from the S1 mod look like. Voila. So if we look at this, so we get an intercept of 0.07. Compare that to our intercept of up here. So it is a little bit different, but it's still around the realm. It's still around the realm of it. You know, it's really a difference of less than 1, really, if you think about it, when you go from negative 0.1 to 0.7. Essentially. So it is around less than 1. And then additionally, if we look at our CalDEF of 0.277, how does that compare to our slope with this? Yeah, so it's relatively similar. So as you can see, it gets around the actual value, not exactly around it, not exactly, but around it. It's not as good as we were at predicting the mean, but we're getting around the actual value. It's kind of the point of it. So when we run these samples, we get something close, but no cigar, essentially. But we're getting an estimate. It's not the true value, but it's an estimate of what the population would be, and we get around it. So let's go ahead and run the summaries on our other models and see how close we got here too. And I'm just going to go ahead and copy and paste, and then do S2 mod, and then S3 mod. So let's go ahead and see what it looks like for our S2 mod. Voila. So here we got an estimate of 0.66. So it seems like a lot, but you have to keep in mind how small of numbers we're talking about. These differences are less than about 2, in all honesty. And then our calorie deficit is 0.19, which is still less than 1 difference between that. So the calorie deficit is pretty close still too. And then we'll go ahead and run our S3 mod, which this one actually seemed to be the closest of all of them. So negative 0.004, so I forget what our 0.1, so it was about a 0.6 difference or something like that, or 0.1, little less than 0.1 difference, and a caloric deficit of 0.279, which our caloric deficit for slope is actually pretty close. So as you can see, we're close but no cigar on all 3 of our models, but that's okay. We're okay with having some error. We expect there to be error in everything that we do. So I went ahead and just ran all 3 of the models, and you can go ahead and look through and see how these models compare to the actual population parameters. And that's really the purpose of today's lesson, is to show you that we're pretty close when we run these regression analysis to the actual population value. And if we were to run and get bigger samples, you can even mess around with it. If you're going to samples of size 200, 300, 500, you would get closer to the actual values if you had bigger samples as well. And that's the entire purpose of this, is to show you that you would get close to the actual values. So that's pretty much it for today's lesson. What I'm going to go ahead and do is show you, go onto module and show you your assignment essentially. So for your assignment today, if you go to modules, load up a little bit, and then go to Module 7 Lab, you'll see that I don't have any data sets. That's because you're not going to be using any data sets. You as well are also going to be simulating data sets here as well. I have 2 versions for you. I have the Module 7 Lab activity in a PDF form, and I also have a version in HTML. The reason I made an HTML version is because, if we'll go ahead and look at this, I'll go ahead and download it. I made an HTML version of the same assignment because when you try and copy and paste some of these things into your R code from a PDF, I find that there's often problems. For some reason, when I convert it to an HTML document, it seems to be a lot easier. So for this, in example, I have you actually copy and paste some code to create your own, data sets, to generate your own data sets and simulations. I'd rather you copy and paste it from the HTML document into your R. So you essentially go open up the HTML document, copy and paste the code when it instructs you to, go to R, copy the code, create a new arc chunk, and paste the code into here from the HTML document. If you want to try it from the PDF dataset, I think it might give you problems, so that's why I'm encouraging you to do it from the HTML document. Okay, everybody. Well, thank you so much for listening in, and that concludes today's lectures, and let me know if you have any questions in lab. Thank you so much.